Okay. Okay, everyone. It's fun to be here, and I welcome everyone who is in attendance. I've given talks like this before. Let me briefly introduce myself. My name is Tom Sherlock. I'm a developer here at Wolfram Research. I work on the user interface of our Mathematica product. But my hobby is doing astronomy. And I like to try to combine work with pleasure whenever I can. And I like to use Mathematica to help me do some of the processing tasks that's necessary for doing astrophotography. I've given talks like this before at um, our Wolfram Science seminars, and I'm going to do the same next month. But right now, I'm not going to talk about my own astronomical observations, but I'm going to talk about how you can process data collected by the James Webb Space Telescope into nice false color images. So let's get started. So let me just get things rolling here. So this is processing images from the James Webb Space Telescope. Now, these images you see right here are ones that I put together using the scientific data, which is all publicly available. This is the Karina Nebula. This is M57, the Ring Nebula, and this is the famous pillars of creation in M16, the Eagle Nebula. So I think it's probably appropriate to do a little background on the James Webb Space Telescope and tell why it's different than, for instance, the Hubble Space Telescope. So let's get started here. This is a picture of the James Webb Space Telescope. Um, James Webb Space Telescope is substantially different than something like the Hubble Space Telescope because it operates in the infrared, which is a wavelength um, at least twice as long as the visible wavelengths that we see with our own eyes. We can see around, you know, 400 to 500 nanometers. The James Webb data starts at about a micron. So, and that explains some of the design features of the telescope. You'll notice that the telescope mirror here, well, in addition to being segmented, which was necessary to fit it into the rocket, it's gold colored. And that's because gold reflects better in the infrared wavelengths. Also, since it is operating in the infrared and hot objects do emit infrared radiation, in order to keep the telescope cold, it has to have a bunch of features towards that end. For instance, this big space uh, thermal shield here, it's multi-layered and it's protecting the telescope from radiation from the sun. Also, the space telescope here doesn't orbit the Earth. It orbits what's called the L2 Lagrange point. So it tries to stay in the Earth's shadow. It's far away. It took a month to get to that point. So it's way out there in deep space. And it also has additional features like cryo coolers and stuff to keep the telescope close to absolute zero, because only then can we get nice noise-free images with the telescope. And as anyone who's done any astrophotography knows, that minimizing noise is one of the biggest tricks. So the James Webb Space Telescope has taken this to an extreme state of the art. So, that's the instrument we're looking at, and I'll talk a little bit more about how it works here. The the data that comes from the telescope is all publicly available, and it's available on this website that was mentioned earlier. Here's a link to the website, and I'm going to put it up here on the screen. It's not the easiest thing to use, but it's not hard either. You can search for a target. For instance, here I'm searching for the Ring Nebula, which is M57, and you can select the the telescope. For instance, here I'm just looking at James Webb data, and I want science data, which not calibration data. And there's a bunch of other things you can do. You can pick out specific filters or instruments, and but right now this is all the M57 data, and you can download any one of these packages, and this will give you the scientific data, which is in the form of what's called FITS files, that you can bring into your computer. And I brought it into Mathematica, and this will let us build our images. Now, it's important to remember that the pretty pictures that you see promoted are not really the purpose of the telescope. It's to collect scientific data. So with some additional work, you can process this data into nice looking pictures, but it's really intended for doing scientific analyses of astronomical objects. So let's get back to our notebook here. So I'll say a little bit more about how the scientific instruments on board the telescope work. Um, Everyone these days has a cell phone, and you're familiar with taking pictures on your cell phone, and the pictures are color pictures. The scientific cameras work a little bit differently. They don't normally take color pictures; they take monochrome images. And that's because that way you can get the maximum data and sensitivity for a given sensor. And when a picture is taken, it's typically taken through a sequence of filters. And the filters are selected to narrow down on specific wavelengths of light, which will give us um, the um, will give us information based on the chemistry of an object. And we can take a series of these images and say one is red, one is green, and one is blue, although they're not really red, green, and blue, and assign those colors to them and create a color image from that. And just in case you're wondering, it turns out that the sensors on your cell phone are also monochrome sensors, but the filters are actually built into the sensor, and they're over alternate pixels. So if you look at your cell phone camera sensor, there's going to be a grid of red, green, and blue filters on top of the pixels. And when you take a picture, you're taking a monochrome image through those different filters, and there's software on your phone or in your digital camera that will synthesize a color image from that. So when we synthesize an image from like the James Webb Space Telescope or other scientific cameras, it's done by taking three different pictures, at least three different pictures, through three different filters, and then just combining them in a straightforward manner with our software, in this case, Mathematica. So the first thing I wanted to try, and by the way, the reason why I got into this talk is because I heard that people had imaged the Ring Nebula, which is one of my favorite objects because it's so easy to find. So they had imaged the Ring Nebula on the James Webb Space Telescope. So I looked up the data, and with some work, I was able to process it into an image, and I sent that around through our mailing lists here at work. And of course, people say, "Oh, wow, that's great, Tom, and we got to make a web posting and write a notebook about that." And pretty soon, here I am. So, so that just shows you that uh, just a little bit of work can get a big splash if you're lucky enough. But anyway, let's talk about the Ring Nebula. The Ring Nebula is a what's called a planetary nebula, and it's the remains of a star that has died. And when the star died, and it didn't go like a supernova, it just basically blew off its outer shell, and there's nothing but a white dwarf left. And so the Ring Nebula, which looks like a ring, is actually the shell of gas that remains from this dead star. So It's easy to find in the night sky because it's close to a very bright star called Vega, which is easily visible in the summer sky. And it's also part of this constellation called Lyra, which is the Lyre. And M57 is right here between these two stars, Beta and Gamma, in Lyra. So it's easy to find in a moderately dark sky. And you can see it with a very small telescope. Um, but typically, when you look at it through the telescope, you're going to get something that looks like this. It's not, there's not a lot of detail in it. You can see, if you have a larger telescope, you can see the ring structure, um, but it's usually kind of a fuzzy blob. So, but let's see what we can do with the data collected from the James Webb telescope. Okay, so as I mentioned, the way the James Webb telescope and all other scientific telescopes work is it is a monochrome sensor, and it takes pictures through a series of filters, and the filters are usually arranged in a wheel. And I've got a similar camera at home, and this is what my wheel looks like at home. You can see there's 5 filters on it, and 3 of them you can assign to red, green, and blue. So the uh, the M57 object was imaged using one of the instruments on the James Webb Space Telescope called the NIRCam, which stands for Near Infrared Camera. And NIRCam is a pretty complex system. It's actually got 2 image sensors, and each image sensor has a pair of what's called a filter and a pupil wheel. And so this is the pupil wheel, and this is the filter wheel. And you can see a series of filters here. So basically, it works exactly the same way as your little amateur filter wheels work, except it's bigger and it's more precise, and it's got other lenses and stuff here. Which, like for instance, this one here is clearly a pupil, which is used to focus the image on the space telescope. Um, I've got a similar sort of pupil mask, but it goes on the front of the telescope. I don't have it on a separate filter wheel. So, and there's 2 sets of these things because the NIRCam can image in 2 different wavelength bands, and each one has a separate set of filters and a separate set of pupil wheels. So these are what the filter ranges look like for NIRCam. There's the short wavelength channel and the long wavelength channel. And there's a beam splitter in the optical path of the NIRCam, which splits the light coming from the mirror into 2 paths, and one goes through one of these filter wheels, the other one goes through the other one. So in this graph here, you can see the wavelength is in microns. And right here, about 0.5 microns is about what we would call red light. So you can see that the wavelength is much, much longer than what we would even consider red light. So it can image in, and this is just the near infrared region. So it can image in these big bands here. And these things here are the names of individual filters in that wheel. So how do we get this stuff into Mathematica? This is all pretty interesting, but how do we get this stuff into Mathematica? Well, the first thing you have to do is you have to go to the website I was mentioning before, and you can pick out, and there's a lot of stuff here. I'm not going to try to remember exactly which files I downloaded because I think they've added some additional stuff, but you can click on these things, and okay, that's still being calibrated. So these are all calibrated products, and I don't want to talk about calibration right now. If you're interested in that sort of stuff, you can uh, listen in on my my talk next month. But you can download anything you want here, and it will give you a zip file filled with the basic scientific data files, these FITS files. And this is an example of the imagery, kind of a rough image that comes in some of these packages. So let's go back to our notebook here. Now, what I've done is I've downloaded the actual and unpacked the FITS files for 3 of the different filters. So this is the F300 filter, this is the F335 filter, and the F162 filter. And you can see here's the F300 filter, here's the F335, and let's see, F162. So F162 is the shortest wavelength here at about 1.6 microns. So I just downloaded this stuff, and Mathematica has the ability to just read in FITS files directly. So I'm just going to put together the names of these files, and now I'm going to import them into Mathematica. Now you'll notice here, when you import one of these, uh, the way it comes in is not as an image, but it comes in as a Mathematica association. And that is because, I don't want to show you the whole thing because it's going to be gigantic, but it comes in as an association, and the FITS files have different segments associated with them. And through some poking around, I realized that segment number 2 is the image segment. There's other scientific data and calibration data in one of these images, but for our purposes, we're just interested in the second chunk of data in these FITS files. So I'm going to load them in here. Now, these are big, high-resolution files. I can't remember exactly what the resolution is, but it's in thousands and thousands of pixels. So we're going to bring them in here. Okay, and bring in this last one. You notice one takes a lot longer to load than the other ones. And I think that's because there are different resolutions. And I'm not exactly sure the purpose behind this, but if you look at the actual um, diagrams of the NearCam system, you'll see that the imager has like 4 sensors on it, and I think for this one they used all 4 sensors, so the image is bigger. And this is good for scientific work, but it's also kind of a nightmare to put the images together, because in order to get the images on top of each other, which is what we need to create a color image, you've got to line them up and scale them. And it's not a simple stretch type of thing. Um, so, but luckily, Mathematica can help us do this without too much trouble. So here's our 3 images. We've just brought them in. And um, so let's look at the F300 image. So here you can see the thing. And you can also see some interesting artifacts, like, for instance, uh, the telescope has 3 um, 3 struts which are holding the secondary mirror, and that causes this hexagonal star-shaped um, effect here. And I think the multiple mirror arrangement also causes some of these other little artifacts, which you might not see in a normal everyday telescope. But this makes it easy to pick out alignment points. And so what I do here is I can use the user interface feature of Mathematica and select points from inside the image. Now, I can't remember exactly which stars I used, but usually, and you can do 2 or 3, you can do as many as you want. The more that you do, the more accurate the alignment will be. But I found 3 is pretty good. So I just picked 3 widely spaced stars, and then you can copy the points to a Mathematica expression. So for instance, here are the 3 alignment points I picked in this image. And in a similar manner, I picked the same three alignment points in the other images. So these images um, are not necessarily naturally lined up, and they're also not necessarily exactly the same resolution. You can see that this image has a bit of a black border here. So you can't just lay them on top of each other. You really have to pick points and do an alignment using Mathematica's image transformation um, uh, functionality. So for the F335 filter image, I picked the same three stars, and I got the same three. Well, I got three different points, which are slightly different coordinates. And this is the F162 filter image, and you can see the images have a lot of hash in them, and perhaps they haven't been fully calibrated yet, but I don't think it's going to matter too much in the end. And you can also see some artifacts here. This might be because this image was built out of the four sensors in the NearCam sensor array. So here's our 3 points for the F162 image. Now we have to be able to, using these sets of points, we have to create um, an affine transform, which will take two of the images and map them onto our reference image. So what we're going to take as our reference image, the F335 filter image. And this is where Mathematica really shines. It's got a function called find geometric transform given two sets of points. And so I can never remember exactly which set is which. So I always go to our little reference feature here. And you can see that find geometric transform will find a geometric transform that aligns position specified by points 2 with points 1. So this will generate a transform which will take the image that was uh, generated the F162 points and align it with the image that generated the F335 points. And in a similar manner, we're going to do the same thing with find geometric transform. They'll take the F300 points and align it with the image that generated the F335 points. So these will generate the two transforms. And this is a very quick operation because it's purely linear algebra. So now that we have the actual transforms, we can use another great function that's part of Mathematica called image perspective transform. And this will take a transform and an image, and it will create a new image that is aligned with our reference image. So this will, we feed in the transform and the image, and it will create a new image, which is called F162 image aligned. And that's the image that is aligned with the 335 filter image. And there's some additional arguments here. It needs full data range. It took me a little while to figure this out. I had to get some expert advice from our image people, but it will scale and rotate the image so that's locked on to the 335 filter reference image. And so I do that with that. And so this will generate two, you can see that was very quick too. This will generate an aligned F162 filter image and an aligned F300 filter image. So now that we've got that, we're kind of home free because now we can just combine the aligned images. And we can do this using color combine. So here we're taking the F335 image to be red, the red channel, the F300 image um, to be the green channel, and the F162 image to be the blue channel. So red, green, and blue. And you can see that color combine will just create a multi-channel image by combining the sequence of channels in the image of eye. And we're using the telling it we want RGB color space. So this is red, green, and blue. And you'll notice that I've picked the longest wavelength image to be the red image, the medium wavelength image to be the green image, and the short wavelength image to be the blue image. Although these aren't really red, green, and blue, they're super deep red, slightly less deep red, and deep red. Okay, so um, and so that's our image, and we just built it there. And this is what the image histogram looks like. And so if we just look at that, um, this is what it looks like. It's a little bright, so I think we're going to need to adjust the image a little bit. So that's, I'm going to do image adjust, and this will tone down the brightness a little bit. And you'll see our final image here. So this is a really nice image of the Ring Nebula. You can see all sorts of detail here. From the gas shell that was expelled by this star when it died. And for your, in case you're wondering, a star about the mass of our sun will do about the same thing when it eventually peters out in several billion years. We'll create a planetary nebula like this. But this is the star in the center. If you have a good telescope, you can just barely make that star out. But here it looks great. And but we can do a little bit more with our image processing tools that are built into Mathematica. Mathematica has a wonderful array of image processing functionality that and computational photography stuff that if you have even the slightest interest in photography or imagery, these are really cool things to play with. For instance, what we can do, we can um, compress the luminance values to create what's called a high dynamic range image. So here we're using color tone mapping, and it will, and we're using color tone mapping with a zero point 0.1 factor here, and you can play around with this. And this will reveal additional interesting details that are not present in the previous image I showed you. For instance, you can see all these streamers and stuff that came off the star ahead of the main shell that you see when you're just looking at normal photographs of M57. So you can see that it's actually much bigger than you would expect just looking at it through a telescope or at a regular picture. And you can also see internal details here, which are probably gas clouds in front of the thing. So it's not really a donut, although it looks like that. It's more of an egg-shaped shell. So that's some of the stuff you can do with this data that comes from the James Webb Space Telescope, and that worked out really good. So I tried it with other um, sets of data. Like when the James Webb Space Telescope was first launched, about 6 months later, after they had finished setting up the telescope and calibrating it and focusing it, they released a very impressive series of images, which were created by teams of people. But we can do pretty almost as good work here, just using Mathematica and some of the data which is publicly available. Like one of the images they released was of the Karina Nebula, and you can get the same sets of. Actually, this was done in a little different way. I didn't download this from the MAST site. There's another site which I will talk about in a later talk that actually has a web API that you could use to download more processed images. And for instance, in this case, it's not downloading actual JPEG images, which are available on this site, which has the REST API. So so anyway, these are the URLs for those particular images, and here, let's see, let's just see if we can, yeah, okay. So now we can import them. We can just import those images directly. And these aren't FITS files. These are, this may take a little while longer to do. Yeah, there they go. Okay, so we got them in. So you can see the, 3 channels here from 3 different filters, a 090 filter, a 200 filter, and a 444 filter. And these are the 3 channels of the Karina Nebula. This is the picture that was released early on, um, about 6 months after James Webb launched. And we can do the same trick that we did above to align them. You can see that they're kind of skewed here, but we can still align them by doing the same trick and picking out a given set of widely spaced stars. So here's our set of points for the red, and here's our set of points for the green. And actually, I messed this one up. So yeah, and I didn't pick them in the correct order. And then here's the set of points for the blue channel. Again, I'm going to find the geometric transforms in exactly the same manner. And then I'm going to transform the channels, and I'm going to so that produced the blue and the green images, and then I'm going to color combine them, and there's our color composite showing the 3 aligned images placed on top of each other. There's a little bit of an alignment error around here. I could have done a little bit better in the picking of the points, but still, it's pretty good for an amateur working for a few minutes. And we can do some other tricks. Again, I'm going to boost the contrast. I'm sorry, boost the brightness a little bit, and that'll bring out further details in the nebula. So the final one I worked on is the Eagle Nebula. This is M16, and this was taken with a different instrument on board the James Webb Space Telescope. Um, this image became very famous back in the 90s because it was shown as one of the famous iconic images produced by the Hubble Space Telescope. This is called the famous Pillars of Creation image in the Eagle Nebula. This is the filter wheel on uh, this other instrument, which is called MIRI for mid-infrared imaging. And so this is, you can see the filters arranged here, and this whole thing rotates, and it brings a given filter in front of our imaging sensor. So that's, and you can see there's other things here. There's a lens here, but that's opaque, probably for doing dark frames. There's some other stuff here, other optical elements. And this is the ranges for the MIRI instrument. You can see that it's quite long. It starts out here at 5 microns and goes up to 30 microns. So this is far infrared. So this is the other one was the near cam, so that's near infrared. This is more of a medium infrared. So again, I downloaded the Eagle Nebula files from the MAST site, and those are my file names. And I I had them in the wrong order here. So I just flipped them around, and I'm just going to import them. And now the good thing about I'm not exactly sure why this is. I think maybe because the image sensor is a little bit simpler on the Miri instrument, but the images that it produces tend to be pretty well aligned. So we don't have to do the image transform tricks that we did with the near cam images. So which was I was very happy for that, but I just managed to just download them and perform a little bit of an image adjustment on them. And here I'm doing the image adjustment just to bring up the contrast, and I'm doing that. So in one step here, what I'm doing is I'm importing all the images, um, and I'm running an image adjust on those. So that gives us the three images. So we can see what they look like. Well, they don't look too impressive right now. This is more of what you typically get with astronomical images. You really have to bring up the contrast and stretch them a little bit, but let's see what we get. But they're pretty well aligned as they are. So let's try color combining them. And let's see here. Okay, still not too impressive. A little murky there. So we're going to have to really boost up the brightness on that. And we can easily do that with image adjust. It's, it's a lot better there. Now we can see the the pillars of creation. And I'm just going to crop it a little bit to get rid of some of these artifacts here. Let's just do that again. Okay, looking better. I'm not sure what's causing some of these dropouts here. These might be bad pixels on the sensor, or maybe these pixels have become saturated or something. So I didn't really do anything to isolate those. People who do this stuff professionally take care of that, because I noticed that isn't visible in any of the published pictures of the Eagle Nebula. Also, the imaging experts who produce these images from the data, they combine more channels, not just three channels, but they might combine six channels, and maybe I'll do that later on once I get that technique down. So anyway, so this is what the things look like. We can sharpen it up a little bit, um, which we use our sharpen tool, which basically does um, uh, blurs the image and then subtracts it out, leaving the high resolution uh, results. So that's what it looks like. It's not too bad. The Eagle Nebula became famous, as I said, when the Hubble Space Telescope published pictures of it back in the mid 90s. And you don't really need the Hubble Space Telescope to see the Eagle Nebula in its glory. It's actually quite visible through a relatively small telescope. Our astronomy club here, we meet regularly south of the city, and from that site, which is not particularly dark, through like a 10 or 12-inch telescope, I could see quite a lot of this detail. You could easily see the Eagle Nebula from a site like that with a moderate telescope. You won't get the sort of detail, of course, but you can still see the thing. And actually, the Eagle Nebula was a fairly well-known image even before the Hubble created that famous picture, as I just realized that it was prominently featured in the first episode of Lost in Space back in the 60s, which kind of dates me, but I do remember this scene. So, anyway, that's that's my little talk about how to generate images from James Webb Space Telescope data. Do we have any questions?
I think there was one question remaining in particular, and you did slightly address this in the discussion of dead pixels. And I have to admit, I shuddered at the idea of dead pixels on on a device like this. It's understandable, of course, but
Well, actually, I think I haven't looked this up for the James Webb Space Telescope, but all CCD sensors have dead pixels. I mean, it's just an artifact of manufacturing chips that
mhm.
large. And you can actually download the dead pixel map. I know you can do that for the Hubble telescope,
Useful.
but I'm sure you can do that for the James Webb telescope too. And that will let you like eliminate those artifacts. But I didn't go to that level of trouble. I was just trying to see
Right,
if I
right.
could combine these images.
Yeah, I guess the actual question, since that was really just me going, the question was related to that, which was, how do these results compare to these official published images, aside from what we just mentioned?
Well, one big difference that I've noticed in the official published images is they're usually made up of more than three channels.
Mm,
Our color combine um, functionality works with three channels. And I'm not exactly sure the process used to produce like a six channel image.
right.
Um, I there I have done a for my own imaging work out in my backyard. Um, I will typically produce what's called a four-channel image, and that takes three color channels through three different filters, and then a fourth uh, image, which is through a clear filter, and that just captures what's called luminance data.
Mm,
And then it's pretty simple to combine um, the the three color channels with luminance data. And the advantage of doing that, and maybe this is what they do on the James Webb Telescope, is you can uh, you can take color data at lower resolution, which combines the pixels into like clusters of pixels for greater sensitivity, but lower spatial resolution. And you can combine that with a high resolution luminance channel to produce an image which has high detail and high color sensitivity. So that's a four-channel image, but I'm not sure how they do it with the six-channel images. So I'm going to keep working on that, and
yeah,
if
that's
and I'll share that with.
yeah. Mapping a six-channel image into an image like this does seem like a difficult and interesting thing to be trying to do.
It's probably not that hard. I just haven't
I guess
played
you have
with
to
it.
make choices, I guess,
Yeah.
is the issue. And those choices to me seem difficult. um, okay, we have a
It,
few
it's
more.
kind of a nerdy hobby, but it's
Oh,
fun.
yeah, for sure. It's a good one, though.
Yeah.
We do have a few more questions here.
Sure.
So I'll go ahead and put this one up so everybody can see it. Donald asks, in the documentation, are there details about the warping images so that we can
The warping
understand
algorithms.
or algorithms, so that we can understand the limitations?
Yes, absolutely. You notice I didn't specify um, the when you say warping algorithms, you're we're talking about computing the transforms from the sets of points. The um, generally the images are not going to be warped. They're going to be either shifted or rotated. That's typical for astronomical images, because you can imagine you take one picture, and then a few minutes later you take another picture and the scene is shifted slightly, or it may have rotated slightly. So astronomical images are either um, they need either a shifting or a rotational transform, and you can handle our image transformation calculation routines can take that into account. You can specify what sort of transform. So if you want to, here I just use the default values, but if you want to get into it a little more deeply, you can specify if you just want a translational transform, or a translational and rotational transform. So that's all in the documentation.
All right, that makes sense. Yeah, I've
Yes.
certainly seen a few of these transformations myself. Not really had much occasion to use them, but they are well documented, like most things here.
Yeah.
And here's kind of a just kind of a nice question to ask. I think,
Mhm.
so it's not a particularly technical one, but I think it provides a nice sense of comparison. So, uh, how do the resolutions of telescopes like the JWST compare to, say the megapixel counts we have on cameras? And of course, there's the question of sensor size, which I'll go ahead and tack on. So, do you know how like large these CCD sensors are?
I don't remember I don't remember exactly the size. Maybe we can find that out. Or let's just uh, okay. So for instance, let's do our um, okay here. So the F-162 image. Let's Okay. So that's the F-162 image is 4,831 pixels by 4,816 pixels. So that's one of the channels. And let's check. Wait. Okay. No, here, this is a good example. You'll see that the different color channels, and this is why something like the M57 image was kind of hard to put together. You can see that the channel taken through the F-162 filter is like twice the resolution of the channel taken through the F335 filter. And I think probably that the F-162 image was done using all four segments of that big sensor.
Hmm.
And I think the F335 image was either done using all four segments and binning the pixels two by two, or just using one of the segments. I don't know the exact details. I would have to look that up. But you can see that the images are different dimensions, and it's possible that they did this to get higher resolution on the channel because they wanted to get more high resolution scientific data through this particular filter when they took this picture. So as I said, the goal here with scientific images like this is not to create pretty pictures, although we can create pretty pictures. It's to actually gain scientific data. So the
Hmm.
scientists who arranged for this observation was interested in the details of what was coming in that band right there. So yeah, this is substantial. It's not gigantically bigger than your uh, your typical digital camera, but it's still
Yeah, pretty
pretty high
detailed.
resolution. And also the sensors themselves are fat. So each pixel, even though the sensor in a
Hmm.
digital camera might be like this big, and the James Webb sensors might be that big, that just lets each pixel absorb more photons.
Right,
So
and you said that it was, it's basically around absolute zero, so that certainly helps.
yeah, yeah.
Lets you do that.
On my little CCD camera, which I have at home, that's got a refrigerator on it too. And
Mm,
I typically cool that down to 0 degrees Celsius before I start taking pictures. But this will cool the
excellent.
cryo coolers on the James Webb will cool it way down. I mean, just that's part of the magic involved with
Mhm.
that telescope.
Right. Yeah.
Mhm,
Okay. So we have a reasonably high resolution image, a huge sensor, and then we have these large pixels that are kept at a low temperature, which keeps thermal noise to a minimum. And so
mhm.
you wind up with, well, suffice it to say, even if the megapixel counts are similar, you wind up with a much better imaging capability out in space. You're also not trying to image through atmosphere, which is very helpful. So you wind up with
Absolutely,
these
yes. That's
incredible
that's
pictures.
that's the big advantage of a space telescope.
Okay. So I don't think there are. Oh, there was one more question. Um, let's
Oh,
get to.
let's see. Rotations are understandable. However, translations for the astronomical distances involved. Translations, again, I'm not sure about. Usually, translations. Uh, well, I can't speak for the James Webb Space Telescope, but in my own imaging, a translation might for a an image would be if my telescope isn't perfectly aligned with like the polar axis, and so the image drifts a little bit between exposures. So in that case there'd be a slight translation of the image from exposure to exposure, and that's why a translation transform is required. Also, there are other types of telescopes which don't use see, my telescope mount is called an equatorial mount, but there's other things called fork mounts, and the image while you're taking pictures will start to rotate slightly on a fork mount telescope,
Mhm.
and that's why rotations might be involved too.
Okay, neat. Yeah, I've seen some of these incredible mounts that rotate and track, and it's just it's very neat to look at.
Yeah, it's really cool, and it's rewarding, but you have to set those things up. And
Yeah.
actually, just as kind of an aside, the uh, when they launched the James Webb Space Telescope, I was amused by that everything that they were doing to get the telescope up and running were things that any amateur astronomer is
Mhm.
also intimately familiar with. Like, you have to take your telescope to a dark sky site, which is what they did, and then you have to put it together, which is what they did. They had to make a telescope that would put itself together, which is
Slight
non-trivial.
challenge, yeah.
It was a challenge. Then they had to line the optics, which you have to do with a lot of different telescopes, and then you're still not done. You have to make sure everything is calibrated, which I do every time I take my scope out. And so these are all things that any amateur astronomer is going to do, and so but they just have to do it at a bigger scale.